All right, problem number 8 from the Praxis 5165 practice problems. This is kind of an interesting problem. I think it's a good problem, actually. We're given two different graphs. F of x is just 3x squared, whereas g of x is ax squared plus b for unknown parameters a and b. And we're asked about the values that a and b would have to take on if we want the graph of g to be below the graph of f for all values of x. Since my goal in these videos isn't to necessarily answer the questions that are asked, but to teach enough so that you do well in the exam, I'm going to use this opportunity to review a concept that's really important and I could see being useful for several problems on this exam, the idea of function transformations. So what's going on with function transformations is you kind of start out with a graph like, I don't know, x squared. And then there's 4 different things you can do to this graph, each affecting this original graph in a different way. I'm going to represent those 4 things with the letters A, B, C, and D. So I got A times, maybe I'll call it CX plus D squared plus B. Weird to go out of alphabetical order, but I want the A and the B to kind of correspond with the A and the B here. So really what's going on is I can either add or subtract if the value of B or D is negative, or I can multiply as you see with the values of A and C. But there's 2 different ways I can add or subtract, and there's 2 different ways I can multiply. I can either add and or multiply values by the input of this function, by the x value, or I can add or multiply the output of this function, the x squared, the stuff outside of the parentheses. And depending on where and how you alter this original function, you can make different changes to the graph of this function. So those changes come in 2 different flavors. There are vertical and horizontal transformations. When you think about vertical transformations, think about the y-coordinate of the graph, which makes sense. The y-coordinate is sort of the height of the graph. When you think about horizontal transformations, you're thinking about the x-coordinate of the graph. There's 2 of each type. And if you can understand all that, you can understand all different types of function transformations, which will answer not just this question, but a lot of similar questions. Let's start with vertical. Those are the easier of the 2. Vertical transformations are transformations that change the y-coordinate of the graph. The y-coordinate of this graph is x squared, so it sort of makes sense that the vertical transformations would be the letters that affect the output, the squared thing. Not the input, the x value, but the thing that's being squared. In this case, the A and the B both correspond with vertical transformations. When you have both types of vertical transformations, the order that you apply them is really important. But the nice thing about vertical transformations is everything kind of works out the way it should work out. If you think about your order of operations, multiplication comes before addition, so it makes sense that we'd apply this transformation before we'd apply this transformation. How do you apply those transformations? Well, let me give you an actual example. Let's do y equals, I don't know, negative 2 times 3x minus 4 squared plus 1, just to throw some random numbers in there. I chose to apply the vertical transformations first. It doesn't matter whether you do vertical or horizontal first, but within the vertical transformations, the order that I apply these to is really important. It's important that I first apply the transformation that corresponds with this negative 2. There's a couple different ways you can describe this transformation, but I think the easiest way to think about it is in terms of addition and multiplication. This negative 2 here just means I'm going to multiply all the old y values by negative 2. That's it. If you look into a book, they'll say you should reflect the graph vertically about the x-axis, and then you should stretch the graph vertically by a factor of 2, which is all true, but I think that that's a lot harder to remember than just, there's a negative 2 right here times this stuff. Why don't I multiply all the y's, y because it's a vertical transformation, by negative 2? Then after I do that, I look at this positive 1 down here, my other vertical transformation. A book will tell you that this plus 1 means that you should shift your entire graph up 1 unit, but what I think is easier is just to think I'm going to add 1 to the y values. Negative 2 times this thing being squared, let's multiply all the y's by negative 2. Then this thing being squared, I add 1, let's add 1 to all the y values. That's it. And as long as that makes sense, horizontal transformations won't be too hard. The only additional thing you need to know about horizontal transformations is everything is backwards. It's kind of the opposite of what you would think you'd do. So with vertical transformations, I multiplied before I added. I did transformation A before I did transformation B. That makes perfect sense. Order of operations, multiplications before addition. My horizontal transformations will correspond with the C and the D here, because those are the 2 letters affecting the x coordinate, not the x squared, the stuff inside the parentheses, loosely speaking. You'd probably think that you should apply C first, because multiplication comes before addition, but you don't. You're actually going to apply the D first, and then you're going to apply the C. Note that I labeled these as 3 and 4, but maybe I should have labeled them as 1 and 2, although that can be kind of confusing. I just want to make the point that you don't necessarily have to do the vertical before the horizontal. It makes no difference at all. It's just within the horizontal, do D before you do C. And within the vertical, do A before you do B. So to make this a little bit more concrete, I want to apply the transformation corresponding with this -4 before I apply the transformation corresponding with this 3. And you're like, all right, I get it. There's a -4 here. Now they're horizontal transformations. So it's not the y value that I'm going to add or multiply by. It's the x value. And I'll be like, yep, that's exactly right. You'd be like, oh, and I see a -4 here. So I bet I'm going to subtract 4 from all the x values. I'd be like, that's good that you're thinking that, but that's wrong because horizontal transformations are all backwards. So when you see this -4 here, you're thinking I probably should subtract 4, but instead I'm going to add 4 to the x values. Not only are the order that you apply your horizontal transformation sort of backwards, but the transformations themselves are kind of backwards. You see -4, you think subtract 4, but you don't subtract 4, you add 4. If this were a +4 here, then I would subtract 4 from the x values. All that's left to do is apply my final horizontal transformation, the transformation corresponding with this 3. You're probably thinking you should multiply all the x values by 3. That would make a lot of sense if these transformations weren't backwards, that's what you do. But they are backwards, so that's not what you do. Instead of multiplying by whatever you see here, you divide. So I'm going to divide all the x values by 3. If you don't want to divide by 3, you can multiply by 1/3. You can multiply by the reciprocal of what you see here. It means the exact same thing. Let's see if that all made sense. If I start out with the graph of y equals x squared, our standard parabola that kind of sort of looks like this. If you want, we can label a few points. When you put 1 in, 1 comes out. When you put 2 in, 4 comes out. When you put 0 in, 0 comes out. -1 in, +1 comes out. -2 in, +4 comes out. Sure, good enough. Now we'll apply our different transformations. Again, it doesn't matter if I do these two first or these two first, but I have to do this one before I do this one. Since I introduced them with these first and these second, I'm going to go ahead and apply them with these first and these second. But maybe you can convince yourself that the order won't matter, because if you move things left and right and then up and down, or if you move things up and down and then left and right, you end up in the exact same spot, right? Walk 3 blocks west and then walk 5 blocks north, and you hang out there. I'm going to walk 5 blocks north and then 3 blocks west. In a minute, we'll be at the same spot. Anyways, I'm going to stare at these 5 points and think about their y coordinates, so not their x coordinates, but just their y coordinates, 0, 1, and 4 respectively, and multiply all those numbers by -2, and then add 1 to what I come up with. So 0 times -2 is 0, and 0 plus 1 is 1. 1 times -2 is -2, and -2 plus 1 is -1. Similarly, this 1 times -2 is -2, and then plus 1 takes me to this -1. This 4 right here times -2 takes me all the way down to -8, but don't forget you have to add the 1, so it ends up at -7, just like this point that starts out with the y coordinate of 4, jumps down to -8, then up to -7. This dotted graph here is what I end up with after applying the 2 vertical transformations of the 4 that I have written in this function. Another way of saying that is this dotted graph pictures y equals -2 times x squared plus 1. Not times 3x minus 4 squared plus 1, because I haven't applied the 3 and the -4 yet. I only applied the -2 and the 1 transformation, so that's what I see here. Presumably my end goal was to come up with the graph of this mess. So what I want to do is take this dotted graph and transform it to include the 2 horizontal transformations. First, I have to add 4 to the x value. So again, we're going to pick on these 5 points, but now we're not thinking about their y coordinates, which are +1, -1, and -7 respectively. We're thinking about their x coordinates, which are -2, -1, 0, 1, and 2. First, I want to add 4 to all of those different x values. So this point used to have an x coordinate of -2. If I add 4 to that, now it's got an x coordinate of +2. This point had an x coordinate of -1. If I add 4, now it's got an x coordinate of +3. This point had an x coordinate of 0. 0 plus 4 is 4. This point had an x coordinate of 1. 1 plus 4 is 5. And finally, the point that was here in red had an x coordinate of 2, and 2 plus 4 is 6, so it ends up over here. That's it, I'm finally done? No, we've applied this transformation, but not this transformation. So to get my final graph, the dotted graph in blue here would be y equals -2 times x minus 4 squared plus 1. We haven't yet applied the transformation corresponding with this 3. Once I do that, I'll finally be done. I'm going to divide all my x values by 3, so I want to stare at this point right here and not concern myself with its y coordinate, which is -7, but instead just think about its x coordinate, which is +2. +2 divided by 3 is 2/3, so we'd end up somewhere over here, a little bit to the left of +1. This point has an x coordinate of 3. 3 divided by 3 is 1, so it's going to end up right here. This point has an x-coordinate of 4. 4 divided by 3 is 4/3, or 1 1/3, somewhere about there on my graph. This point has an x-coordinate of 5. 5/3 is 1 2/3. And then finally, this point, which had an x-coordinate of 6, 6 divided by 3 is 2. So this point's going to end up over here at +2, -7, a point that's been used several times. Maybe I need to connect some dots so you can see what the hell happened. My final graph, given by this equation, is shown in blue here. I think the first time people see these, they kind of don't like doing things the way I described them up here. They prefer to be like, well, first what we did is we flipped this graph over and then we kind of stretched it out and then we shifted it up 1 unit. That was sort of all the red transformations. And then for the blue transformations, we moved it to the right, and then we kind of smashed it back in towards the axis. And that's all true. Those geometric interpretations are fine. But if you think about this just according to the geometric transformations, there's 6 different types you have to remember instead of just 4. And some of them can be a little bit ambiguous. This idea of compressing things horizontally often confuses students. They kind of compress everything in towards the axis of symmetry as opposed to towards the y-axis. In my experience, thinking about things this way, even if maybe that's not the way you learned it, is a lot easier for transformations. The cool thing about function transformations is it's not at all specific to y equals x squared. You can start out with whatever the hell graph you want. It doesn't matter, right? You could start out with, I don't know, y equals the log base 3 of x. Sure. Think about how we'd apply each of our 2 different types of vertical transformations and how we'd apply each of our 2 different types of horizontal transformations. Maybe this is a good time to pause. Can you put in an a, a b, a c, and a d for this graph instead of x squared so that the a, b, c, and d would have the same transformations as they did in our example? What I'm looking for, maybe I didn't describe that very well, is a times the log base 3 of cx plus d plus b. The a and the b are 2 vertical transformations. They're affecting what comes out of this graph. The y-coordinate, the log base 3 of x. The c and the d are the 2 horizontal transformations. They're affecting the x-coordinate directly. If we started out with, I don't know, the square root of x, we could transform that vertically by having an a outside the radical here and a b outside the radical here. And we could transform it horizontally by having the cx plus d in here. One more, if we had the reciprocal graph, y equals 1 over x, we could transform it vertically by having the a over here and the b over here. And we could transform it horizontally by having the cx plus d down here. Anyways, if that makes sense, you understand function transformations generally, which is way more powerful than anything you need for this specific example, because for this specific example, we only have the a and the b. So all that's going on is we're transforming this thing vertically, not horizontally. Maybe I can draw a picture. Let's again start out with the graph of y equals x squared. I'll scale my axes a little bit so that it's easier to see my graphs. Y equals x squared goes through the origin, 0, 0, goes through 1, 1, and -1, 1. It goes through 2, 4, and -2, 4. That's nothing you have to memorize. I'm just picking some arbitrary x values and squaring all those numbers to get the graph of y equals x squared. That's not either of our graphs, f of x and g of x. F of x is 3x squared. But even without our calculator, we could figure out exactly what that looks like. This 3 is a lot like our a up here. This is not y equals 3x squared. This is 3 times x squared. If I put 10 into this machine, for example, the 10 gets squared and I get 100, and then I multiply 3 to get 300. I don't do 3 times 10 and get 30 and find 30 squared being 900. This 3 is a vertical transformation. To apply it, I'm going to multiply all my old y values by 3. 0 times 3 is 0, 1 times 3 is 3, 4 times 3 is 12. Similarly, this 1 times 3 is 3, and this 4 times 3 is also 12. Geometrically, the effect that this 3 has is it stretches the graph vertically, but you don't need to memorize that. Just multiply all the y values by 3 and see what the graph looks like. Finally, the question: what are all the real values of a and b for which the graph of g of x equals ax squared plus b below the graph of f of x for all values of x? I think the way I would answer this question is I would go through a, b, c, and d, and in each case, see if I can draw a graph with the given constraints on a and b that gets above the graph in green. And if I can, then that's not my answer. So first, for a is greater than or equal to 3 and b is positive. Can I draw a graph where the value of a is greater than or equal to 3 and the value of b is positive so that that graph gets above the graph in green? Yeah, that'd be pretty easy. I mean, there's millions of answers, but one of them would be 3x squared plus 1, maybe? right? 3 is definitely greater than or equal to 3, and 1 is definitely positive. For answer A, I can consider the graph of y equals 3x squared plus 1. It would look just like the graph in green, except after I applied all these first type of vertical transformations, I'd have to apply my second type of vertical transformations, where I'm adding 1 to the y coordinate. So I'm taking all these points and I'm adding 1. I'm shifting them up a little bit. It ends up looking like this, loosely speaking. Is the graph in pink always below the graph in green? No. In fact, the graph in pink is always above the graph in green. So I came up with a graph that satisfied the criteria given in part A here, that is certainly not below the graph of f of x, so this is most certainly not my answer. What about B? What if A is less than or equal to 3 and B is negative? Okay, let's see. First, I'm multiplying by a number that's less than or equal to 3. The biggest it could be was 3, but if it's exactly 3, I have this graph in green, and then since B is negative, I'm going to be subtracting some amount from all these points in green. So that's going to end up moving them down. That'll certainly leave me below the graph in green. But that's just one value of A. That's just if A is equal to 3. What if I don't make A equal to 3, but I make it smaller, like 2 or 1? Well, think about what would happen if it were 1 or 2 or something. I'd start out with the graph in red, and I'd multiply all the y values by something that's less than 3. So if it's like, I don't know, 2.9, then the points end up really close to the graph in green, but slightly below them. If it's like 2, well, then the points end up somewhere between the line in red and the line in green. If it's 1, then I'm exactly on the line in red. If it's 0, then I end up with the horizontal line here, y equals 0. And I don't have to stop at 0. What if it's negative? Well, if it's negative 1, my graph would end up looking something like this because I'm multiplying all the y values by negative 1. If it's negative 2, now it looks more like this. Negative 3, now it looks like the graph in green, but flipped upside down. So when A is less than or equal to 3, I end up with the graph that takes on, I don't know, kind of one of the shapes, one of the many shapes that you see in pink here. So the question is, can I take any of these graphs that I start out with in pink and get above the graph in green if the value of B is negative? Well, remember, for our order of operations, we want to apply the A transformation first and then the B transformation. And the B transformation, that just tells me how much I'm going to add to all the y values. If B is negative, I'm going to be adding a negative number to all the different y values. In other words, I'm going to be subtracting from the y values. In other words, I'm going to be shifting the graph down. So take any of these many graphs that you see in pink and shift them down. It doesn't matter how much you shift them down by, they'll always be below the graph in green. What I'm trying to say is, if A is less than or equal to 3 and B is negative, we can come up with a wide variety of graphs, but all of them will be below the graph in green for all different x values. B is a correct answer. Let's go through C and D and make sure that those don't make sense. For C, A is a negative number. So what that means is we're taking the different y values and multiplying them by some negative number. If it's like negative 10, our graph kind of looks like this. If it's negative 1, our graph kind of looks like this. Kind of. But regardless, we have this parabola that kind of opens up downward. Don't know exactly what it looks like, but something like this. Oh, but the value of B is positive. So after I apply this first transformation, then I'm going to add some number to all the different y coordinates. It doesn't even matter what that number is. As long as it's a positive number, the point that starts out at 0 is going to end up above the graph in green. So for example, y equals, I don't know, negative 2x squared plus 1. That'll do the trick. The negative 2x squared leaves me with a graph that looks, loosely speaking, like this. But then the plus 1 shifts it up 1 unit. I end up with the graph that kind of sort of looks like this. Note that pink is above green. That means C is not the right answer. Lots of different counterexamples showing that C is not the right answer, but one would be y equals negative 2x squared plus 1. Finally, D. A is any real number and B is negative. Can I pick a value of A and a value of B so that the graph that I end up with after my transformations gets above the graph shown in green at some point? Sure. Just make A a big number, right? If A is, I don't know, 10 or something, well then this point that had a y value of 1 now has a y value of 10. This point that had a y value of 0 still has a y value of 0 because 0 times 10 is 0. This point which had a y value of 1 now has a y value of 10, again, because 1 times 10 is 10. This point, which had a y value of 4, now has a y value of 40, so way the hell up here somewhere. If I put a 10 in place of the A, I'm multiplying all the different y values by 10. I'm stretching the graph vertically so that it ends up looking something like this. B is a negative number, but that's okay, I don't know, just make b like -1 or something. All that's going to do is subtract 1 from these different points, moving my graph in pink down a tiny bit, but it's still above the graph in green for most x values. Kind of dips below here at 0 and really close to 0. But for all the other x values, pink is above green. Pink is certainly not always below green. Therefore, D is not the right answer. I think that this function transformation approach is probably the best way to answer this question. If you didn't know function transformations, well, you might still be able to get this specific question right. You could just kind of play with your graphing calculator and plug in different values and see if you can come up with a graph that satisfies the given criteria. But the problem with that is they don't tell you the values for A and B. They give parameters for those numbers. So you don't really know what to plug into your calculator when trying to graph things. If you don't know how A and B affect the graph, you might have a hard time guessing and checking your way into a graph so that that graph gets above the graph in green at any point. The other reason you might want to do it this function transformation way is because this method will work on a wide variety of problems. If they made g of x equal to y equals cx plus d squared, totally different than this function, I could still answer the questions. If I didn't start out with the graph of x squared, but I started out with the graph of the square root of x or any other graph, and they asked me to transform it like I see in red over here, I could still answer the questions. And even questions with sort of a different general layout. Function transformations are really powerful. It kind of connects functions in an algebraic perspective to functions in their graphs. And I really think it's something you should review before you take this test.